So students, so dear friends, today I have brought about a concept in which we will explain effective magnetic moment of lanthenides, that is how to determine G value and effective magnetic moment of lanthenides. Basically two questions have been asked from this concept previous yearly. In 2016 a 4-marker question has been asked in which we were asked to determine the value of G for cerium 3 plus and promethium 3 plus. And then again in 2014 a 4-mark question was asked in which we were asked to determine the ground term of SM3 plus and europium 3 plus. I'll suggest you one thing: if you want to solve any question from lanthenides or actinides, basically you have to at least remember electronic configuration of lanthenides. If you remember electronic configuration of lanthenides, you can at least solve 70% of questions in any competitive exam based only on electronic configuration. Now let us go to our topic, how to determine G value as well as effective magnetic moment. Basically in case of lanthenides, we determine this effective magnetic moment. It's equal to G under root of J into J plus 1. This is the formula. G under root of J into J plus 1. We have to first determine value of G and J values. Now what are these J values? We'll come to know a little later. And what is this J what is this G value? We will come to know a little later. Now how to determine this G value? This G value is equal to 1 plus S into S plus 1 minus L into L plus 1 plus J into J plus 1 divided by 2J into J plus 1. Don't fear about the formula. It looks like to be lengthy formula, but it is very easy. Now see, 1 plus S into S plus 1. S is the spin value of an electron. L is the orbital quantum number value of an electron. And J we can determine from the value of L and S. Now see, we are basically going to determine over here a term called the term symbol. We represent a term symbol by the formula L J 2S plus 1. Now what is this value of L? This value of L, if it is equal to 0, 1, 2, 3, 4, 5, etc. We use the terms. For L is equal to 0, we have S term. For 1, we have P term. For 2, we have D term, F term, G term, H term, like that. Means we are basically first determining value of L. If L comes out to be 0, it is S term. If it comes out to be 1, it is P. If it comes out to be 2, it is D. If it comes out to be 3, it is F, and so on. Now this S value, S is the spin of an electron. It can be plus half or minus half. Depending upon how many electrons we have, we can then add them. We can later on add them. Now J value is equal to, J we have of two types. J can be L plus S. J can have L plus S value. L plus S is used when the configuration is more than half filled. When we have more than half filled configuration. When we have more than half filled configuration. And we can use L minus S. It is used when configuration is less than half filled. Whenever we have configuration less than half filled, we use J is equal to L minus S. And when we have configuration more than half filled, we use configuration J is equal to L plus S. Now let us determine value of G, and then we can determine effective magnetic moment. Let us solve this question. Let us determine from this question. We have a question: determine value of G for cerium 3 plus and promethium 3 plus. Now let us determine for cerium 3 plus. The question is determine G value for cerium 3 plus, Ce3 plus. We know that cerium is a lanthanide element having atomic number 58, means we have xenon, 54 atomic number. Then we have to fill 4 electrons. They are 4f1, 5d1, 6s2. Now remember one thing, there are only 4 species in lanthanides where we have d1 electron. That is lanthanium, that is our cerium, that is gadolinium and lutetium. In all other cases, there is D subshell does not contain any electron, and 6s subshell contains 2 electrons. Then we have to fill up only electrons in F subshell. Now see, we have cerium 3 plus over here. By cerium 3 plus I mean 3 electrons have been lost. Therefore configuration is 4f1. Now by 4f1 configuration, I mean that we have a configuration like this. We have 4 f orbitals. We know that we have 7 4f orbitals. 7 f orbitals 1, 2, 3, 4, 5, 6, 7. Now there is only one electron. That electron is over here. Now we have L values. This is 0. This is plus 1. This is plus 2. This is plus 3. This is minus 1, minus 2, minus 3. Now see, there is only one electron. Therefore our S is equal to, we have only one electron. Therefore our S is equal to, I can drop over here. We have only one electron, therefore S is equal to half. For one electron it is half. If we have one more electron, then we have to add up. If there is pairing of electrons, then we can use 1 half minus 1 half. Since I have only one electron, therefore spin is equal to 1 half. Therefore S comes out to be over 1 half. Now we have to determine value of L. Value of L we will determine for a ground term. We start filling electrons over here. It can have different values. But for ground term, when you are determining G value, use like this. First electron over here. For this, L is equal to plus 3. Over here, L is equal to plus 3. Now we have to determine value of J. J is equal to either L plus S or L minus S. Since in this case, configuration is not half filled, it is less than half filled. Therefore, J is equal to L minus S. L we have 3, S we have 1 by 2. That is 3 2s are 6 minus 1, that is 5 by 2. Therefore, J comes out to be 5 by 2. Now we can easily determine G value. Now we can easily determine G value. G is equal to 1 plus S into S plus 1 minus L into L plus 1 plus J into J plus 1 divided by 2J into J plus 1. This is the formula from which we can determine G value. Now we know that S is equal to half, that is 1 plus 1 half into 1 half plus 1 minus L is plus 3, that is 3 into 3 plus 1. J is 5 by 2 plus 5 by 2 into 5 by 2 plus 1. And we have 2J into J plus 1, 2 into 5 by 2 into 5 by 2 plus 1. Now we are going to solve it. Now see, 1 half plus 1 is equal to 2 1s are 2, 2 plus 1 that is 3, 3 by 2. 3 by 2 into 1 by 2 that is 3 by 4 means 1 plus 3 by 4 plus 3 plus 1 4, 4 into 3 minus 12 plus 5 by 1 plus 1, 2 1s are 2, 5 plus 2 7, 7 by 2, 7 into 5 35, that is 35 by 4. Let us do it. 5 by 2 plus 1 is equal to 2 1s are 2, 5 plus 2 that is 7 by 2. We have to multiply it by 5 by 2, that is 35 by 4 plus 35 by 4 divided by 5 by 2 plus 1 that is 7 by 2. 7 by 2 into 5 by 2 5s are 10 by 2 into 10 by 2, that is 70 by 4 divided by 70 by 4. This is 1 plus. This is G value. Now see, here what we are going to do to make it more easier, we are going to make bases same. In order to make bases same, 4 over here, 4 over here, 4 over here, we have to multiply it and divide it by 4. 12 4s are, now 12 4s are 48. This will become equal to 48 by 4. If we write this 12 equal to 48 by 4, that's actually 12. Now see, we will write it like that. 1 plus 3 by 4 minus 48 by 4 plus 35 by 4 divided by 70 by 4. Now it becomes easier. Bases are same, powers are added. Now see, 35 plus 3 that is 38. 35 plus 3 that is 38 minus 48. 48 minus 38 that is 10. Or we can write it in detail. That will be equal to 1 plus 3 minus 48 plus 35 divided by 4 divided by 70 by 4. Now further solving, this will be equal to 48 minus 3, 45 plus 35, that's minus 10. This will be equal to 1 plus into minus 10 by 4 divided by 70 by 4. Now take this on the upper side, we can have This will be equal to 1 plus minus 10 divided by 4 into 4 by 70. Now 4 and 4 will go. 10 1s are 10 7s are. We get 1 plus into minus minus 1 by 7. 7 1s are 7. 7 1s are 7. 7 minus 1 is equal to 6. We have 6 by 7. Then the G value comes out to be 6 by 7. Now G value of this cerium 3 plus comes out to be 6 by 7. Now it becomes more easier now. Now you can easily determine their effective magnetic moment. Now from this you can determine effective magnetic moment, mu effective. Now mu effective will be equal to G under root of J into J plus 1. Now from this you can determine mu effective. Now mu effective will be G is 6 by 7. Now J, what was J? J was L minus S. What was S? 1 by 2. What was L? It was 3. 3 minus 1 by 2, that's 5 by 2. Under root of 5 by 2 into 5 by 2 plus 1. So this will be equal to 6 by 7 under root of 5 by 2 plus 1, that is 7 by 2. 5 ones are 5, 2 ones are 2, that's 7 by 2 into 5 by 2. That is 35 by 2 under root of 35 by 2. You can solve it now later. Similarly, you can determine G value for promethium. Let us determine G value for promethium. Let us determine G value for PR3 plus. Now PR3 plus has atomic number 59. PR configuration is 4F2, 5D0, 6S2. 4F3, 5D0, 6S2. Now we have PR3 plus. In PR3 plus we have 4 F2 electrons, means we have 2 electrons in the F subshell. Now by 2 electrons I mean that we have 1 electron over here, 1 electron over here. This is 0, plus 1, plus 2, plus 3, minus 1, minus 2, minus 3. Now see, in this case S will be equal to 1/2 plus 1/2 because the 2 electrons have same spin. That is 2 by 2, that is 1. In this case L will be equal to 3 for this electron and 2 for this electron. I am determining ground term over here. I will take the concept of term symbols in a separate video where I will show you if I put this electron over here, then what happens to the term. Now see, in this case 3 electrons over here, 2 electrons over here, 3 value for this electron, 2 value for this electron, that is 3 plus 2, that is 5. Now determining value of J, since the configuration is less than half filled, J will be equal to L minus S, that is 5 minus 1, that is 4. Now we determined 3 things over here. S is equal to 1, L is equal to 5, J is equal to 4. Now we can determine value of G. Now the value of G will be equal to 1 plus S into S plus 1, that is 1 into 1 plus 1, minus L into L plus 1, L is 5, 5 into 5 plus 1, plus J into J plus 1, 4 into 4 plus 1, divided by 2J, that is 2 into 4, into J plus 1, that is 4 plus 1. Now it will be equal to 1 plus 1 is 2, that is 2, minus 5 plus 1 is 6, 5s are 30, that is 30, 4 plus 1 is 5 into 4 is equal to 20, divided by 4 plus 1 5, 5 into 8 is equal to 40. Now it will be equal to 1 plus, now see, this is 28 plus minus 28 plus 20, that's 8, minus 8 by 40. Now 8 1s are 8 5s are, this comes out to be 1 minus 1 by 5. 5 1s are 5. 5 minus 1 by 5, that is 4 by 5. In this case G value comes out to be 4 by 5. Therefore the answers for this question were 6 by 7 and 4 by 5. This was the correct answer. This is how we can determine G value. Now one more question was asked, in which we have to determine ground term for samarium 3 plus and europium 3 plus. Now let us determine, because basically these two concepts are related. I'll determine here, I'll solve this question as well, in which I have to determine ground term for samarium 3 plus and europium 3 plus. Now we know that samarium has atomic number 62, europium has atomic number 63. In case of samarium, the configuration is 4f6, 4f7, 4f6, 5d0, 6s2. In this case, we have 4f7, 5d0, 6s2. Basically, these two species are very important. Now, why they are very important? A large number of questions in CSIR net have been asked on this fact: samarium 3+, samarium 3+, and europium 3+. I think it should be samarium 2+. Let us see, it is samarium 3+. Now, in this case, samarium 3+, we have 3 electrons are lost, 2 from here, 1 from here. We have 4f5 configuration. Now we have to determine ground term. Now see, it is very easy. It takes only few seconds to determine ground term. 1, 2, 3, 4, 5, 6, 7. We have 5 electrons. 1, 2, 3, 4, 5 electrons. Now we know that this is 0, +1, +2, +3, and this is -1, -2, -3. Now we have first to determine S. S will be equal to 1/2 + 1/2 + 1/2 + 1/2 + 1/2. Basically 5/2 half. 1/2 + 1/2 + 1/2 + 1/2 + 1/2. Half for all electrons because all have spin up. That is S is equal to 5/2 half. 5/2. Now we have to determine value of L. L value will be equal to summation of these L values. Now see, for this it is +3, +2, +1, -1. Now we have +3, +2, +1, -1. This and this will go, we have +5. L is equal to +5. Now when L is equal to 5, we know that ground term is when L is equal to 0, 1, 2, 3, 4, 5, 6. We have S, P, D, F, G, H. Since L is equal to 5, therefore term is H. Since L is equal to 5, S, P, D, F, G, H. S, P, D, F, G, H. 0, 1, 2, 3, 4, 5. Since L is equal to 5, therefore term is H. We use the term H. Now we have to determine J value. Since the configuration is not completely filled, it is not half filled, it is less than half filled, J will be equal to L minus S. Now L is 5 over here, S is equal to -5/2, 5 2s are 10, 10 minus 5 is 5/2. Therefore term for this becomes, samarium 3 becomes, we have H and we have J equal to how much? 5/2. J equal to 5/2. Now we have to determine over here 2s plus 1. Because I already told you that the term is represented by this 2s plus 1. We have determined S to 5/2. Therefore, it will be H 5/2. 2 into, what is S? S is 5/2. 5/2 plus 1. 2 and 2 will go. 5 plus 1 is 6. Therefore, term is H 5/2, 6. This is the term for samarium 3+. I hope you can determine term for europium 3+. Or let me show you how we can determine term for europium 3+. How we can determine term for ground term for europium 3+. Now europium 3+ means we have europium in +3 oxidation state. However, the most stable state of europium is +2, but in the question it is given europium 3+, therefore we have to take it. Otherwise we can't form europium 3+ because it has a stable configuration over here. Or you can determine it for europium 2+. Let me check the question correctly. Is it europium 2+ or 3+? It is given 3+. It should have been 2+, but it is given 3+. Let us determine 3+. Now 3+ means 2 electrons lost over here. 1 electron lost over here. It is 4f6. Now take 4f6. 2, 3, 4, 5, 6, 7. 3, 6, 7. 1 electron. 2, 3, 4, 5, 6. 6 electrons. 0 plus 1 plus 2 plus 3. -1, -2, -3. Now first determine value of S. Since all have same spin, 1/2, 1/2, 1/2, that's 1, 2, 3, 4, 5, 6, 6/2. 6/2 is equal to 3. Now here we will also determine 2s plus 1. 2s plus 1 is equal to 2 into 3 plus 1, that is 7. Therefore, whatever answer, our answer will be at the top, there 2s plus 1 of that answer should be 7. Now after that, we have to determine L values. L values will be equal to summation of these L values, that is plus 3 plus 2 plus 1 plus 3 plus 2 plus 1 minus 1 minus 2 minus 1 minus 2. Therefore L is equal to 3. We know that if L is equal to 0, 1, 2, 3, 4, 5 terms are S, P, D, F, G, H, etc. Now L is equal to 3, therefore term is F. L is equal to 3, therefore term is F. Now L is equal to 3, therefore our term is F. We have F term. Now the question comes out to be L is F term and it is 2s plus 1 is equal to 7. This thing we have solved. We can check our answer from this thing as well, but we will determine J value as well. J will be equal to L minus S. Why L minus S? Because this configuration is less than half L. Now we know we have determined L was equal to, L is equal to in this case 3 and S is also equal to 3, that is 3 minus 3, that is 0. This is the ground term. This is ground term. Therefore ground term is F07. This is ground term. Now how much easy it is. Now the most important thing is we have determined, we have used the formula to determine effective magnetic moment of lanthenides. Effective magnetic moment of lanthenides. We have determined it from the formula G under root of J into J plus 1. This G we have calculated from 1 plus S into S plus 1 minus L into L plus 1 plus J into J plus 1 divided by 2J into J plus 1. But there are two important lanthenides, that's europium 2 plus. This thing you have to remember. This is very important. 3-4 times the question has been asked. Europium 2 plus and samarium 2 plus. Europium 2 plus and samarium 2 plus. This magnetic moment which we calculated over here, it is called calculated magnetic moment. Calculated magnetic moment, effective magnetic moment. These two ions, they differ from this effective magnet. They do not obey this formula. Means they show difference from this formula. Whatever magnetic moment we calculate for europium 2 plus and samarium 2 plus, from this formula, that is mu effective, from this formula mu effective, from this formula, this it differs from experimental value. Experimental values are different. Experimental values for mu of these two ions, they are different. Means the observed value, the calculated value and the experimental value are different for only two ions, that's europium 2 plus and samarium 2 plus. All other lanthanides ions obey this formula. Only two do not obey the formula. They deviate from this formula. They do not, in that case, in europium 2 plus and samarium 2 plus, the calculated magnetic moment and the experimental value, they are not same. This is very important. This question has been directly asked. The calculated value and the observed value are not same for which of the following lanthanide ions. So it is very important to remember. Europium 2 plus and samarium 2 plus deviate from this formula. In europium 2 plus and samarium 2 plus, the calculated magnetic moment and the observed magnetic moment are not same. Why they are not same? There is a reason for that. Now see, in europium 2 plus and in samarium 2 plus, the observed magnetic moment mu observed, that is observed from experiments, mu observed, that is not equal to mu calculated. That is not equal to mu calculated. The observed magnetic moment is not equal to mu calculated. The observed magnetic moment is not equal to mu, means samarium 2 plus and europium 2 plus deviate from this formula. They deviate from this formula. Now why they deviate from this formula? Because the difference in, they deviate because this is very important. This thing has not been asked. This has been asked. The difference in ground state and excited state is very small. That means delta E is approximately equal to kT. This is very important. This has not been asked. I hope this may be asked because questions are frequently asked. They have touched almost everything. This thing they have not touched. The difference between ground state and excited state, first excited state, it is almost small. It is very small. It's all delta E is almost equal to kT. Now what is this delta E and kT? For this you have to study Boltzmann distribution law, where that betterly understands relation between delta E and kT. Now see, this is the difference. Now in this case, in case of europium, the more important things you have to remember, in case of europium 2 plus, mu effective comes out to be 0, but mu observed, experimentally observed, it is not 1.0. It is not 1.0. Mu effective comes out to be 0. It is not 1.0. It is different from that. Mu effective from this formula G into under root of J into J plus 1 comes out to be 0 for europium 2 plus, not 3 plus, for europium 2 plus it comes out to be 0, but experimentally it is not found to be 0. Experimentally its value has been found to be, let me check it so that I cannot give you wrong information. Its value has been found to be 3.4. It's 3.4. That's why it differs from this formula. Now why this discrepancy, why this happens? Because in europium 2 plus, this magnetism arises, mu arises because of first excited state. First excited state means you have to first excite electron, then only magnetism can be shown there. Now this can arise only in first excited state. Why first excited state? Because difference between first excited state and ground state is very small. Therefore, electrons can be easily excited to first excited state. Now see why. Europium 2 plus have D7 configuration. Europium 2 plus has D7 configuration, 5, 6, 7. Now for D7 configuration, our L value will be equal to 0. This is plus 1, plus 2, plus 3, minus 1, minus 2, minus 3. Our L value will be equal to 0. Now if our L value will be equal to 0, that will not later on give rise to orbital momentum to the electron. Orbital momentum of an electron will be quenched over here. We will not have orbital momentum of an electron over here. Orbital momentum of an electron will be quenched over here. That's why there is difference. That's why we have to excite an electron. Now in samarium 2 plus, mu effective and mu observed also differ. Mu effective and mu observed. Mu effective is equal to 0.845. Remember these values. Sometimes directly it is asked the mu observed value for europium 2 plus and samarium 2 plus are, and mu observed value is 1.74. Now in this case, this magnetism, this value arises because of temperature independent magnetism. Temperature independent magnetism. And in samarium it arises because of temperature dependent magnetism. Temperature dependent magnetism. Now two things you have to remember. In europium 2 plus, mu arises because of temperature independent magnetism, and in case of samarium 2 plus, mu arises because of temperature dependent magnetism. Now basically approach has been changed by CSIR net exam. They give you 2, 3 or 4 statements and you have to pick out the correct statements. They can give you question like this. In europium 2 plus, magnetic moment is because of temperature independent magnetism. In samarium 2 plus, magnetic moment is because of temperature dependent magnetism. In both europium 2 plus and samarium 2 plus, magnetic moment, experimental observed magnetic moment is because of temperature independent magnetism, or in fourth option there will be temperature dependent magnetism. That's why this question becomes very much important. Since it has not been touched, I hope this question may be asked in coming exams. Thanks for watching this video. If you get benefited from my lectures, then please comment and like my channel. and also share my channel. Thanks for watching this video. Now in this lecture we have discussed two questions which have been asked in competitive exams CSIR, and the questions which will be asked in CSIR from this topic. Thanks for watching.